Start recording. Oh, you got to share.
Hey, listen. Ladies, let's move. Get to class. Also, good morning.
Also, good morning.
I can't, Kayla.
Look, we got stuff to do, okay? Gotta go.
Okay, so we're gonna pick up where we left off, which is composition of pure substances. Basically, this is just talking about empirical formula. Now, you guys were good at this when we did it, but it's been let's see, this is something we go over in like November of the honors curriculum. So here's my thing. I'm guessing that this is a little dusty. However, I also think that this is very unlikely to be asked on this now abbreviated test, because this normally only showed itself as a multiple choice question anymore, but we'll still go through it. And then if you need refreshers, there's the videos and stuff. So there's Taylor. Okay, so a couple of the foundational ideas here. The law of definite proportions. This was one of Dalton's things. It basically says that a chemical formula is always going to be made of the same elements in the same proportions by mass. So even before they knew about atoms specifically, they knew that you always maintain these ratios, which means if the chemical formula is always going to be the same ratio by mass, you can use mass to find the chemical formula, which is all you are doing with the empirical formula calculation. So, for instance, if you took those two percentages, do you remember what to do from that point to get an empirical formula from those two percentages? Anybody remember what that is?
Okay, do we have to
empirical
convert the percentages to decimals?
You don't actually have to do that.
Okay.
Well, if you so like if if it's a percentage, right? So they're both, when added together, make up 100% of the thing, right?
You divide the larger by the small.
No, not here. So we would take that 11.9% or 11.19%, and remember we change it just to grams.
Oh, okay.
Do you remember that?
No.
No?
I mean, if that's what you do, that's what you do.
That's what you do, right? And 88.81.
This is so much worse than your iPad.
I know. But once you remember that the percentage is grams because it's percent by mass, what is the only thing we can ever do to grams?
Change it to moles.
Change it to moles. All right, so then it's like from here, you would change to moles. And that would just be by dividing by its atomic mass, right?
Mm-hmm.
And then from there, it's simply divide by smallest mole.
Yeah.
And that's what gets you those ratio subscripts, right? So you divide by the Smallest. That's an ugly yes. Okay.
So dividing by the smallest mole gives you what?
That gives you the subscripts in the chemical formula.
Okay.
So, I mean, I'm not gonna write it out, but like 11.19 divided by hydrogen's atomic mass would give you 11.08 moles, right? 88.81 divided by oxygen's would give you 5.55. So the smallest mole is 5.55. And if you divided 11.08 by 5.55, you're gonna get 2. And that's the correct formula for water, right? 2 hydrogens for every 1 oxygen, H2O.
Mm-hmm.
So because you divide, okay, because of just the way division works, you say like 2 of the smaller ones went into the,
Yes.
and that's how you get the subscript.
Yep.
Okay.
Wait, so you don't divide the 88.81 by 5.05?
No, you divide the 88.81 by 16 to get the 5.55.
Okay. Oh, okay. And then
Yeah.
you just divide the smallest thing by that, and
Yep.
then
Yep. All right, so, you know, our empirical formula, it's the simplest ratio. All right, if you need a refresher on how to calculate empirical formulas, I would watch one of those. Again, I don't think that this has a high likelihood of being tested. It could, but I think it's a calculation, if you don't remember, is not going to be super critical. But doing what we did, if you have those percentages, now let's try and do that question. So you've got your calculators and such. I'll do it on, so you try it on your own there. I'm gonna do it on the board, my dry erase board, and then I'll show you when it's over. Has anybody looked up the atomic mass of barium yet?
No.
It is 137.33.
Thank you. Does that work look familiar?
Yeah.
Like,
yeah, I just didn't know. I didn't know if you were just gonna divide all of them, but now I see you do.
Yeah.
I thought you did, but it wasn't confirmed.
Uh-huh.
Someone's asking, what's the difference between... Actually, let me stop lying. Never mind. I got...
Wait, Ms. Baskin, why'd you divide it by the 0.5067?
This is the smallest small.
Got you.
Also, for C,
Uh-huh.
because it's so close, so you just left it as 1.
Oh, yeah. Like, I didn't even actually enter any of those in a calculator. I'm like, oh, yeah, that's essentially the same number. All right, so since you can look back at this later, since I'm recording, I'm gonna put this down because it's heavy. Okay.
A real trooper.
Okay. Now, the second one, do you have to do anything different?
No.
No, because it would have ended up in grams anyway.
Right. The only difference is instead of taking the step of switching out the percent signs for grams, they've already given you grams. So it's the exact same thing, right? Just you've got two different elements, divide them both by their atomic masses, and you would find that those are basically the same thing, and you'd have carbon monoxide if you were doing that. Okay. Composition of mixtures. Nobody is exactly sure what this topic means or why it's on here because they've never asked any sort of questions on it.
That's gotta.
Well, I mean, that's fine. It's less for us to worry about, right? Like, I'm okay with that. So we're just gonna kind of move beyond that because the last handful of topics is, I think, what needs more dusting off, because you're still used to, even if you haven't done a specific empirical formula problem, you're still used to dealing with grams and moles and that sort of stuff. That's fine. This is a completely different thing, the rest of these topics, and I want to make sure that we spend time going through them. So the structure of an atom and electron configurations. This is literally what I am doing in honors right now. This is what you were doing a year ago. Whether or not you remember what this is a different story, but that's okay. So all of this stuff about atoms, like anything about atomic structure, periodic table, trends, like any of that stuff, it is all governed by Coulomb's law. And Coulomb's law just means the attraction between charges. Okay, so everything is governed by the attraction between charges. So the force here, this F, is the force of attraction. The R squared on the bottom is the distance. So since that's in the denominator, if you have a large distance, what does that mean for your force?
It's small.
It's very small. That makes sense. If you're holding a magnet far away from your fridge, is there very much attraction?
No.
No. Okay. And then the numerator there, the particle charges, remember, that's like the strength of your magnet. So there's a difference between like the free pizza delivery magnet that they give you versus like those tiny super strong magnets. Like, just because it's a magnet, it's not the same. So the higher that particle charge is, the stronger your force is going to be. So those are the things that come into play here. So you have to remember opposites attract, like charges repel. That should be review. And that distance makes your force go down. All right, so that's, again, common sense. Then this thing. effective nuclear charge. I wrote this as Zeph. Z effective, which may or may not ring any bells. But it's basically...
Yes, it does.
Okay. How much attraction do your valence electrons actually feel? And the reason that we're only caring about valence electrons is because those are the only ones involved in doing anything, right? So it's basically, see, there it is, Zeph. It's your atomic number minus your number of shielding electrons. And the shielding electrons is what I've described as that inner core, everything that is not valence, okay? So they're never going to ask you to calculate that. That is not what they talk about. But effective nuclear charge does come into play when we're talking more about periodic trends. So does that look familiar?
Yes.
Okay.
I wish it didn't.
You wish it didn't. Why?
I never liked this part right there. The 1s, 2s, 2.
It was really tragic because I missed it when you first explained it, and so I had to come back. So I was real behind.
So, do you remember how many electrons S holds?
2.
Yes, with the 2 arrows.
All right, it holds 2. What about
Empty
P?
bus seat. I'm sorry.
Yep, empty bus seat rule. There you go. P holds how many?
6.
D
10.
and F?
That one. 11.
12? No.
I don't remember F.
Wait, isn't it 14?
It is 14.
Period.
Yes.
Okay, so there's two ways to remember this. Number one is that there's the exact same gap between them all, right?
Mm-hmm.
The difference between 2 and 6 is 4. Between 6 and 10 is 4. So between 10 and 14 is 4. They go up by 4 each time. That's one way. And then the other way is this periodic table. Like literally looking, and you see that on the far left side, there's 2 columns because S holds 2. On the far right side, there's 6 columns because P holds 6. The transition metals, there's 10 columns because D holds 10. And you remember the pull-out part at the bottom of your periodic table is 14 if you count it across. So what we know is that electron configurations are not going to be asked in terms of write out the electron configuration for blah, 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 because you can pull up the answer to that question on Google in 10 seconds. So that's not what they're going to be asking. They could be asking a question, however, about how electron configuration is related to something around the periodic table. So if you don't remember how to do electron configurations or how this sort of color block arrangement is on your periodic table, since you get to use your periodic table, I would take out some colored pencils and I would color code your periodic table and make some notations around it like this, right? Like you don't have to obscure all of the stuff on the elements, but you can very quickly color code your periodic table to make it very obvious when you are looking at an element how to figure that out. Does that make sense?
Yes.
I still have my periodic table from Honors Chem 2 years ago.
Yeah. Sean. Yeah. Okay. So you remember how to get all these things?
Do
Protons,
you have to
neutrons,
do the
electrons.
1s, 2s thing until you get to 74?
All right, well, that's if it was asking you for the electron configuration. This is just straight plain asking you for the number of protons, neutrons, and electrons.
So don't you find the thing, it's germanium GE.
Yeah.
And so it has the number 32.
Okay, so what does 32 tell you?
32 protons, 32 electrons.
Right.
Right, because it doesn't, if it does not tell you it's an ion, assume it's a neutral atom.
And then you just subtract 32 from 74 because that'll give you the amount of neutrons.
Okay. Yep. All right, Darren.
Oh, yeah, you.
Okay, now the electron configuration for K plus. So here's what I want you to start off with. Write the electron configuration for potassium, for just plain old potassium.
Miss Baskin.
Yay.
Is this, so when we do the electron configuration, this isn't like the actual circles. This is just like the line of numbers, right?
Yes, it's simply the line of numbers.
Okay, because I think I got it.
Okay.
Yep. Wow, it's all coming back to me. That's so scary.
Right? So that guy,
Beautiful.
and my 2s and 5s and S's like all basically look interchangeable. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So that's if it was K, but it wanted K plus. So putting that plus there, what does that mean for my electrons?
It takes away one.
All right, that means I lost one. Which one am I losing?
The 4s.
The 4s1. Okay, and do you remember what element that represents?
It would represent the one right underneath it, right, or something. It'd be
Argon.
Argon.
It's
Okay.
based on the oh my gosh, the gases, the noble gases. Oh, because then you can do it like you can go down and just do the noble gas plus the other thing.
So
Sean, I'm so proud of you.
Epiphany.
So AP does not care which format you use, and I taught you both, and I said I didn't care which format you use, so you can write out the full electron configuration. You can also use what's called the core configuration, right, which is putting the noble gas in these brackets as this core and recognizing that it is what is beyond or outside the core, that valence, that this is what you lose or add into, right? That's where that stuff is coming from. So when we talk about effective nuclear charge or something, it is this core of electrons. That core provides shielding, right? That's your big fluffy pillows that are protecting, protecting stuff.
So when you do the ion, can you still just write it as K plus equals argon?
I don't see why not.
Okay. And then also when you're doing these, isn't there a thing like when you go to D that you have to like drop down a number?
Yes.
Okay. Is that in the video? Because I don't want to take too much time or anything.
It might be. It might also be in the next example.
Okay.
I think I marked it I sent my periodic table to you.
Okay, thank you.
I sent both. I have 2 that both are just like jammed with a bunch of stuff on them.
Okay. What can be said about the ionization energy of the element above? You remember what ionization energy is?
The energy it takes to take away the electron.
Yes. Okay. So if we were talking about potassium with that little 4s1 electron, would that have a high or a low ionization energy for that 4s1 electron?
Low.
It would be fairly low. But once it becomes the ion, right, that 1s2, 2s2, 2p6, 3s2, 3p6, what can we say about the ionization energy of that ion?
It would be higher.
It would be stronger.
It would be high. It would be very high because it's it's
a full
there you go,
full layer.
right? So once it becomes the ion, it's going to have a super, super large ionization energy because it has now matched a noble gas, which is the point of becoming an ion.
That
Okay. All right. So reminders about that. Then once I taught you electron configurations, we went to PES, photoelectron spectroscopy. And
I could
said,
never read that thing. I could
Okay.
not read it.
Well, here's the thing. One of those diagrams has been on each of the last 3 years' exams. So we need to be able to read the damn thing. Because what I can imagine is that they would be more likely to show you a PES diagram, have you write the electron configuration from that, and then answer some other questions that you would have to write out, like this about the ionization energy and that sort of stuff. Like, that's a more likely scenario. So we need to be able to read the PES diagram. The nice thing is they're only going to use those diagrams up to a certain point because they get too big and they're too difficult to read. So we're really talking about only elements of the first 20. And the only thing you have to remember about PES is it is the experimental justification for electron configurations. Like, the spikes in the diagram are the electron configuration. So you have to remember a couple of things about these diagrams. So when you look, the first thing to notice is where mentally are you supposed to imagine the nucleus?
The beginning.
Oh,
At the beginning, right? And
Wait, why at the beginning?
because it's, well, if you look at the values on the x-axis, you see the bigger number is actually on the left, because that peak at 1s is the closest thing to the nucleus, which means it is feeling the most attraction to the nucleus and would require the most energy to pluck off the atom.
Mm-hmm.
So you have to imagine that the nucleus is right there next to the 1s, because that's the only thing that makes sense to have the higher energy value numbers on the bottom being so far to the left. So really the only thing that you have to remember is that the very first peak in these things is 1s, because that is what literally every single electron configuration starts with, which means the size of that first peak is the size of 2 electrons, and you compare everything else to that. So if you have a mental memory of the order of electron configurations, it is the same thing as you see across here. So the first peak is 1s. The second peak, because the second thing we write in electron configurations is 2s, is the exact same size. When we write electron configurations, the next thing after 2s is 2p, and does that peak at 2p, that very last one, does that look like it is 2 or 3 times the size of the 2s?
3.
3. So we would probably say that that's 2p6. That's the sort of estimating that they're going to have you do. So, all right, so the position of the peak is how close it is to the nucleus, and the height is the number, okay? So it's literally just practicing reading these things off. So looking at this guy, let's figure out what that electron configuration is. So the thing above 1077, you'd write what?
1s.
1s, and above 70.9?
2s.
2s.
And above 51.6?
2p.
2p.
2p. All right, and then let's go ahead and put numbers. So it's not just one S, it's 1s2, 2s2, 2p6. All right, then above 23.73,
3s2.
3s2. And now you're going to have to estimate, what do you think the 18.24 would be?
My screen's blocking it.
3p.
3.
3p3.
3.
It's not twice as high.
Yeah.
Twice as high would be 4.
Mm-hmm.
So it's less than twice as high, so we assume it's 3.
I see. Okay.
Okay. And then what element is that?
What is phosphorus?
And how did you get that?
So I looked at 3p3 basically, went down to the third row, and then I went to the P side, so I went past the S2, and I went to the 3p, and the third one over is phosphorus.
Right. So that's using your periodic table method, saying, okay, it's in the third period down. That's what the 3 tells me. It's in the P block. That's the right section, and it's the third one over. That's phosphorus. That's one way to do it. The other way is to simply add up the exponents. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 3 is 15. Atomic number 15 is phosphorus. Okay? So either of those methods gives you the right thing. Okay, so that's PES, right? It's actually really not that hard. Periodic trends. This is where you ended the year. Talking about attraction, shielding effect, effective nuclear charge, and we talked about ionization energy, atomic radii, ionic radii, and electronegativity. They have thrown back on for this year electron affinity, which we did not discuss last year. There's some subtle differences between electron and affinity and electronegativity, but it's not that big a deal. So do you remember off the top of your head what the largest element on the periodic table is?
Francium.
Francium. Yeah. Okay. That is literally the only thing that is down towards that end. All of these other trends are in the opposite direction.
Mm-hmm.
All right, so your ionization energy is the opposite end. The element with the highest ionization energy, helium.
Yes.
It's the tiniest and it's a noble gas. Electronegativity, who's got the highest electronegativity?
Fluorine.
Fluorine, likes to eat your face. Guess who also has the highest electron affinity?
F.
Fluorine, like it's not that big a deal. In terms of the ionic radius, do you remember which one gets smaller, cations or anions?
No idea.
You got to remember what a cation is versus what a anion.
Cations are positive.
Is it
Right.
cations?
Like they're usually metals.
An anion.
Wait, so would it be cations? Because you're getting more electrons as you go down?
Well, it is cations,
But not for that reasoning.
correct. So what happens to give you a positive charge?
Losing
You lose
electrons.
electrons.
Losing electrons. So you're taking stuff away. You get smaller.
Oh.
There's a more detailed explanation than that, but like that's the easy way to remember, right? You're taking stuff away, you get smaller. Anions, you're gaining electrons, you're gaining weight, you're getting bigger. Like that's the simple way to remember it. And then there's actual explanations around attraction that make it go. But that's our thing there. That's our chart. Right? Atomic radius is down there. Electron affinity, electronegativity, ionization energy, all of that stuff is in that direction. And if I remember correctly, on that blank periodic table that we annotated in the previous year, I think we put that stuff on there.
Yeah.
Not 100% certain, but there you go. Okay, so the more detailed explanations, right? Atomic radius, as you move left to right, it gets smaller. This is the one thing that tends to repeatedly trip people up because your atomic number is getting bigger. So people want to say the atom gets bigger, but it does not. It gets smaller. And the reason is that your effective nuclear charge is increasing, and therefore it's pulling everything closer. So a larger atomic number left to right really just means more effective nuclear charge. Does that seem familiar at all?
Yeah, but so would that mean, I know we said francium being, I don't know if francium being the largest has anything to do with this, but so wouldn't, like something like hydrogen,
Mm-hmm.
like wouldn't it have a pretty large atomic radius?
No,
Oh,
because it only has one energy level.
Oh, okay.
Right? So, but it's weird to think about comparing hydrogen and helium, right? These are our two smallest elements. Between hydrogen and helium, which one is smaller?
Helium.
It's actually helium, which is counterintuitive because it's got twice as much stuff. So why is it smaller? Well, because the twice as much stuff is twice as much attraction, and so it pulls everything in closer.
Tighter. Okay.
So that's kind of what it is. So it does sometimes boggle the mind that tiny little lithium on the left-hand side is bigger than neon all the way over on the right, but it is. Not a whole lot, right? When you're looking at things like left and right, it's not a huge difference, but it is a difference. Down a group is easy to think of because I keep adding extra energy levels. And every time I add an extra energy level, I have more and more cushioning around my nucleus that's protecting those valence electrons, right? So I have another whole layer that pushes my valence electrons farther and farther and farther away. Okay. All right, cations are smaller because we took electrons away, so now you have more attraction to the center. So you always have to remember when you're talking about ionic radius, you have to imagine that I normally have equal numbers of protons and electrons. When I all of a sudden become an ion and that number changes, whichever one of those is bigger is the direction of my attraction. So in a cation, I now have more protons. So that means the direction of my attraction is in towards the nucleus where the protons are, and it pulls in tighter.
Oh.
Yes.
Okay. No, I'm understanding.
Okay. And that happens because like the extra amount of protons in comparison to electrons means that my electrons aren't pushing against each other and they can't fight off the protons. On the flip side, if I have an anion and I am adding more electrons, well, now my electrons outnumber. And so they're kind of pulling out in that direction. And so I've got this extra amount of electrons on the outside that are repelling against each other and pushing farther and farther out. So it's really cations are smaller because there's more attraction in. Anions are bigger because there's more repulsion out. Ionization energy, we already said this is how much energy is required to pluck an electron off. So you have to relate ionization energy to size. So my smaller elements are on the right. If I am smaller, what does that mean for my amount of attraction? Do I have more or less?
Less.
More.
What?
Because my distance is smaller.
Oh, between me
Right?
and the next thing.
Yes. So the bigger factor in talking about the force of attraction is distance. Distance matters pretty much more than anything. So if I am smaller, there is a smaller distance between the two things that are trying to be attracted, which means there's more attraction. So if ionization energy is trying to literally pluck something off, if they're really, really attracted, it's going to take a lot more energy to pluck off a thing that's really attracted.
Mm-hmm.
Okay. So all of that is basically saying what I just said.
And when you say, like when you're saying from the distance, are you saying like the distance from the center of the thing?
I'm saying the distance from the nucleus to the valence electrons.
Okay. Okay, yeah.
Okay. And ionization energy decreasing as you move down a group is super obvious because as I'm moving down a group, my atoms are getting bigger, 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 which means the attraction for that valence electron is rapidly decreasing, making it super easy to pluck off. Remember, francium is so reactive because he's so big and fat, he just simply can't hold on to his valence electrons. Like anybody can take his valence electron. His ionization energy is so low.
It's like a fat guy with a donut.
Yes, easy to, I mean, you're not wrong. Okay, so that last bullet point is kind of the gist, right? A smaller atomic radius equals greater ionization energy. Okay, so electron affinity technically is the opposite of ionization energy. So it's how much energy is released when you gain or add on an electron instead of how much energy is required to remove one. It's kind of a weird thing. So basically it's another, you should literally just kind of think of electron affinity as electronegativity. All of the trends are exactly the same and it's still just talking about attraction. So it's like, I don't even really want to talk about it. I just kind of want to move on to electronegativity. All right. So technically electronegativity is attracting electrons to yourself in a bond. And if you remember that fluorine's my most electronegative because fluorine essentially has the most attraction. So electronegativity is another way to remember the amount of effective nuclear charge, because effective nuclear charge is kind of another way to say attraction. So fluorine's got a high effective nuclear charge and it's got a super high electronegativity. So they kind of go together. That's why fluorine is not just so super attractive, it's also super tiny, and so that's why it can steal everybody's electrons.
Thief.
And that's how it melts your face, right?
Yes, that's why
It
fluorine
like
melts.
steals you.
But that's
Okay.
also how fluorine can snatch electrons or, like entice the noble gases to actually bond because its electronegativity is so ooh la la, so high. Okay. Okay. So out of those 5 elements, looking at your periodic table, who's the biggest?
Wait, sorry.
Why? Is it why? No, wait, no, X.
4. What did that say?
Between RB, CD, PD, CL, and SI?
Oh,
I can't read.
I can't read questions. Rubidium.
Rubidium. Out of all of those, rubidium is the closest to francium.
Yes.
Yes.
I need to write all of it on my periodic table so it's real quick.
Yep.
That's so I can just be like, boop.
And then out of all of those, who would have the highest electronegativity?
CL.
CL, because that's the closest to fluorine.
Mm-hmm.
Right. And then, do you at all remember how to read a chart like this?
Of ionization energies?
Uh-huh.
I can try.
So, pointing out here, actually, you see the difference in number between the first and the second ionization energy for X and how big that is? Do you remember us referring to that as the quote-unquote big jump?
Yeah, so you'll be jumping from beryllium to boron.
Well, it means that this first electron is a valence electron, but the second electron
isn't
is not, is a core electron. So for Y, where is the big jump for element Y?
Between
Or,
E2 and E3.
between 420 and
Yeah, between 420 and 3548. So how many valence electrons does it have?
2.
2. So if it's a second period element, which element is it if it has 2 valence electrons?
Beryllium.
Beryllium.
Wait, how do you know that there are 2 valence electrons from the big jump? Like, how did we get that?
Because the big jump was between pulling off a second and a third electron, which means that the second electron was still a valence electron, but pulling off a third electron means that you are pulling off a core electron. So therefore it only has 1 and 2 valence electrons before you hit core.
So, but why wouldn't you say it was, because is it saying like you don't have the E3 and E4? Because then why is it not carbon? Because there's 2 more electrons.
Well, beryllium has 4 electrons total.
Oh.
Yeah.
So it would just be like, so as you like go down, or you have more electrons, this will just get longer and longer.
Oh yeah, yeah.
Okay.
Okay. And the last topic, valence electrons in ionic compounds, is basically like, you know how valence electrons and charges are related and how to cross charges to write ionic compounds? Yes?
Yes.
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 Right. So if you have element X with that electron configuration, what is element X?
Fluorine.
Fluorine. So what compound is it going to make with lithium?
LIF.
LIF, right? So LAX, right?
Lit, bro.
Yeah, there you go. Okay, so I'm gonna stop my share. Class should be over. So we've gone through the review, and Friday's class, we're going to practice with free response questions. And those free response questions I'm going to pick are going to be based around the periodic trend stuff, talking about attraction, because that is the most likely scenario for them to ask questions on in relation to anything in Unit 1. Cool?
Yes.
Well,
Okay. So I'm going to stop recording